Okay, so here we have a problem involving a box and an inclined plane. So usually in these problems, the first thing that you want to do is draw a diagram, which I have here. And once you do that, you want to draw a free body diagram for the block to try to figure out some of the quantities dealing with it. The first thing we have here is a gravity force, or mg. Then we have a normal force, which is perpendicular to the plane. And then we have a static. So in the first part of this question, they're asking about static friction, which means that the box isn't moving. And the static friction is going to be up the plane, kind of keeping the box in place here. That's our static friction there. And in the beginning, they ask what is the value of the static friction force and what's the value of the parallel F. So the thing with the parallel F is our mg isn't very useful to us here because it's not in the same plane as our normal force and our static friction force. Our normal force and our static friction force are perpendicular to each other, but our mg isn't in that same plane. But what we can do is we can split it up and actually make the components in the right direction. So we'll have a y component that's in the direction of the normal force. We'll have an x component that's in the direction of the static friction force. Let's label those x and y. And then we know our theta is our smaller angle here. This is our right angle, and this is going to be our theta. So that's kind of like our mini diagram for our mg force. And now, if we look at the first question, they ask what is the value of the parallel F? Well, the parallel F, they're just asking for the force of gravity that's parallel to the incline. In this case, that would be our mgx. So our mgx, we can get from our little mini diagram here. It's going to be equal to mg times sine theta, because our x component is on the opposite side of our theta. So sine is opposite over hypotenuse. So we know that we have sine theta here, mg sine theta. That's going to be our answer for the parallel component. And I'm going to solve in all variables because it's a lot cleaner. And even when you do problems, you should solve in all variables and plug in at the end so you don't have to deal with real numbers the whole time. But I'm not going to be plugging in this video just to keep it a bit concise. That's going to be our mgx, and then they ask for the value of the static friction force. So for that, we're actually going to need a force statement. And our force statement is going to be that mgx minus our static friction is going to equal 0 because they're in opposite directions and they have to completely cancel out in order for there to be no acceleration and for the block to not move at all. So our mgx is just going to be mg sine theta, and that's going to be equal to our static friction. So our static friction is actually also equal to mg sine theta. We're going to get the exact same answer there. Now for part B, they're asking if the ramp is lifted to 40 degrees, what will the acceleration of the block be? So here we're sort of implying that the ramp is lifted enough to overcome static friction. So now we're going to have kinetic friction. So this is going to change to kinetic friction here. And now there will be acceleration down the ramp. So in order to solve for that, we need to do both a y direction and an x direction. Since with our y direction, we find normal force, and then we use that normal force to help us figure out our friction force in the x direction. So in our y direction here, we have n, which is positive, then we have minus mgy, which is negative. That's going to equal 0, since even though there's acceleration, the acceleration in the y direction with respect to the plane is 0. It's not moving in that direction. So that means that n equals mg cos theta this time, because our y in our mg diagram is actually adjacent to our theta. So that's our normal force. Then in the x direction, we have that our force of gravity, so our mgx minus our kinetic friction this time is going to be equal to ma. The reason why I made mgx positive is because our acceleration is down the plane, so it's a bit nicer to make your positive direction down the plane. So mgx is positive, our friction force is negative because it's opposing it, and that equals ma. So our mgx is just going to be mg sine theta again. Then our fk is going to be our mu k times our normal force. So mu k mg cos theta. We already found our normal force with our y direction, and that whole thing's ma. We can cancel out our m's since every term has an m. Then we can factor out a g. So g times sine theta minus mu k cos theta. And that's going to be equal to our acceleration here. And we can just plug in our theta as 40 degrees and then our mu k, and we would be able to solve for this. So that's the acceleration. Now they ask how long will it take to reach the bottom of the ramp. In order to find that, we need to use a little bit of kinematics. So we need to know this distance down the ramp here, and we can actually solve for that using a triangle, namely sine theta equals h over d, because we're using the whole ramp as a triangle here, which means that d equals h over sine theta. Now that we have the distance down the ramp, we can use a kinematic equation. Delta x equals, and we don't have any initial x, we're setting that as 0. We don't have any initial velocity, so all that's left is 1/2 at squared. In this case, our delta x's are d, so h over sine theta equals 1/2 at squared. We already know a, we solved for it, so then we just have to solve for our t. So t equals, we can multiply by 2, we can divide by a, and we can take the square root. So 2h over a sine theta, and then the square root of that. And that's going to be our t, that's going to be our final answer for the time that it'll take to reach the bottom of the ramp. Then finally, they ask what velocity will we leave the ramp at? So we can use the kinematic equation v final equals v initial plus at. We don't have any v initial, so we're just going to have at. And we know our a, we know our t, we've already solved for both of those. So we're basically plugging in at each step here, and then we're using the quantities that we know to find the other quantities. And yeah, that's basically how you do this, and other problems involving inclined planes and blocks. So I hope this helped. Bye.